Hello, everyone. We've been talking about the electromagnetic spectrum, and we're talking about Wien's law and the spectrum of black bodies here a little bit today is one of the things that we're doing. And so with this light bulb, we've got a solid filament in the light bulb. You can maybe see the coil of the filament there. Maybe if I take it, you'll see it shaking around. I don't know if you can see that coil there or not. So there's a solid filament. We run a current through it, it gets hot. The more current we run through it, the hotter it gets. And the temperature changes, and it glows more and more. So I'm going to change the current by changing the voltage difference across, the potential difference across the two wires that lead into the filament right here. And as I start to turn this up, you'll start to see this glow just a little bit. I think you can probably see that sort of deep orange-red glow right there. I'm turning it back down a little bit now. So you have a very red glow in this filament. As I turn the potential up a little bit more, get a little bit more current, it turns more orange. And as it turns more orange, you see it followed by more yellow. And I keep turning it up, and it keeps getting hotter and brighter and hotter and brighter. And you see it getting more and more and more, really more or less white at some point here, where it's glowing so brightly. You're seeing all of these different colors of the spectrum, and you see the colors with such intensity that it really looks white, all of these colors added together, and brighter and brighter and brighter here, and just keep going up a little bit. You know, that's a really bright light bulb, and you got a really nice white glow right there. We start to turn it back down and watch it get yellow, and as it gets more yellow, and then eventually become more orange and more red again as the temperature gets cooler. Two things going on. Temperature is changing, and that's the one thing that's going on, but it's causing the light bulb to change how bright it is, and it's causing the light bulb to change what color it is. So let's talk about each of those things just a little bit. Let's look and see what we can do with this, thinking about this just a little bit to say, okay, first thing that we're going to look at is to think about Wien's law, and think about Wien's law, Wien's displacement law, in terms of the color of the light bulb, and to say that this light bulb, the spectrum that we get from this dense object, the intensity, remember that's what a spectrum is, it's intensity as a function of wavelength. So it is a graph of that intensity, and you can see something like this. It might not be actual intensity here, but it's something related to that. You can always graph how bright it is at a given wavelength. And that black body has a spectrum that has a peak. And that peak says occurs at a particular wavelength. And that wavelength of maximum emission, lambda max, is equal to 2.9 times 10 to the minus 3 meters Kelvin divided by the temperature of the black body of that filament in Kelvin. So what happens is as the temperature goes up, the maximum wavelength of emission drops. It gets bluer. And so you see this one-to-one relationship like we saw, this inverse relationship like we saw with frequency and wavelength related to speed. So you'll see this thing getting redder as it gets cooler and bluer as it gets hotter. So that's the first thing that we see going on there. The other thing that we see happening is that the total energy emitted we call the luminosity. And the luminosity is equal to this measure. We're not going to do much with this in this class, but this is a measure of how good a black body this item is. We'll take that to be 1 for most of the things that we're doing, times a constant here. That's the Stefan Boltzmann constant. We're not going to worry about that too much. You can look that up. It's certainly in your book. Times the area of the thing doing the emitting, times the temperature to the 4th power. So very sensitive to temperature. That's what we saw going on with the light bulb. Tweak the temperature up just a little bit, it gets bluer, but it also emits a lot more light. It gets a lot brighter, okay? And we'll take the area, if we're working with stars, we're going to approximate stars to be spheres, okay? Whether they are or not, we're going to take this to be spheres. And if they're spheres, we can say 4 pi r squared is that surface area of the star. So then we can say luminosity new divided by luminosity old, or luminosity 2 divided by luminosity 1, is the emissivity sigma 4 pi r squared nu t to the fourth nu divided by E sigma 4 pi r old squared t to the fourth old. And all those constants go away. And so the ratio of the brightnesses of two stars, for example, or one star as it undergoes evolution, is r squared t to the fourth, good grief, r squared t to the fourth divided by r squared t to the fourth. So there are two things that can change that brightness of that star, the radius and the temperature. And so if the radius gets bigger, the star gets brighter as the square of the radius. If the temperature gets bigger, the star gets brighter as the temperature to the fourth power. Okay, so let's look at that. Let's suppose some star got half as big, half the diameter, so R is 1/2 of R initial, but the temperature doubles, and so T is 2 times T initial. So you have some star that undergoes evolution, it gets 2 times hotter and 1/2 the size. Okay? This is an odd stellar evolution, probably not something we're ever going to actually see, but this is just a test case for us, a model to see. We put in 1/2 here, and so nu divided by old is 1/2. You square that, and you get 1/4. So this factor makes the star 1/4 as bright as it was. This goes in here, and you get 2 to the fourth. 2 times 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth power is 16. So times 16. So these two factors together, this made the star 1/4 as bright, this made the star 16 times brighter. So if somehow this happened to a star, or if you were comparing two stars that had these parameters, you would end up with a new star that was 16 over 4, 4 times brighter. Okay, that's the kind of scaling relationships we're going to do, is to ask what happens to stars' brightnesses as they change, as the parameters of these things change. So this is what we're working with here with our spectra, and we'll have lots more to talk about with line spectra and Doppler shifts and other things too.